All right. Cool. Thanks. Okay. A lot was promised. We shall see what is delivered. But this is a talk about AI, LLMs, and economic research. Okay. So, because it was said to be super non-technical, I thought we would start with some pictures. So, this would be a neural network. This is the typical geometry of a neural network. Do we have a line on this? Oh, excellent. Okay, so this is the input layer, and this is a hidden layer, and this is the output layer. This is usually how neural networks are constructed. You have some inputs that you want to put in, and this could be any number of things. A typical example is some sort of digit recognition. Let's say you write the numbers 1, 2, 3, etc. on a piece of paper, and then you want the outputs to say, okay, look, that's a 4 or that's a 6, something like that. The way that that's usually done is that you collect this image, you turn it into a black and white picture, then you represent the whites with 1 and the blacks with 0. You have a sequence of 1s and 0s. Basically take an image, break it by row, and then you have these numbers, feed that into the neural network here, then some magic happens, and then the one for 2 goes, yes, that's a 2, right? That's usually how it works. Okay, so we'll talk a little bit more about exactly how that works. Now, to begin with, first of all, right, and I know it was, I know I was not supposed to do this, but that's why I did not share the slides ahead of time. So you cannot decide not to come because I will show things like this. But yes, you will remember that when we had the discussions with the people from Cube AI, right, they very briefly mentioned that a neural network is a universal approximator. And again, fundamentally, to some degree, we are all mathematicians, right? And it's an important question to ask, why should we believe something like a neural network can identify digits? Right? That seems to be a good question, right? Because I cannot just put, I don't know, a block of cheese and ask it to identify numbers. Right? There's something special about a neural network. Okay? And mathematically, this result is the reason. Now, I will not go too far into the details, but it's a little bit like a polynomial approximation. Right? There is a mathematical result that says that if I have an arbitrary function, and you can, now I can choose a polynomial of sufficiently high degree so that I can approximate this function with arbitrary accuracy. Right? It's the Weierstrass theorem. So here, this is essentially a very similar idea. So you see here, there is a supremum norm, and that goes less than epsilon for any epsilon greater than 0. Fx is the function, gx is this thing, right, which is a sigmoid function on ax plus p. Later, I'm going to call these are the inputs, these are the weights, and these are the biases. Okay, so you would have heard something about, oh, so what's the output? This is the output. And what I'm saying is that if this is the function you want to approximate, there is a neural network approximation to a function as long as it's continuous and from Rn to Rn, there is a neural network approximation that gets arbitrarily close for certain choices of A, B, and this constant C. Right?
So do you choose A and do you choose C?
Yes.
So you choose.
You also choose M and N essentially. Yeah.
And you choose C, capital C?
Yeah. You choose that.
C is the matrix?
So C is in our M cross K matrix. Convolver essentially. Okay. So I don't want to get too much into details about this, but the fundamental thing that I want to drive home is that there is a reason to believe that a neural network can do arbitrary approximations from Rm to Rm as long as f is continuous. So there is a reason to believe that I can throw arbitrary things into a neural network and something good will come out of it. Right? This is a GIF I stole off the of Google Images to kind of give you a visual representation of what happens. Now, the thing to do is to look here, right? Remember I said something like a sigmoid activation? So this is a sigmoid activation. So what is happening here is that there are some inputs, right? There are some weights, and then these weights get multiplied with these inputs and are fed into this net input function. There is some bias that is added, and then with these, there is a real number that is sent across to this sigmoid function. And then this is in fact precisely how brain neurons behave as well, where there's an input coming in. Beyond a certain point, the neurons decide to either fire or not fire. Okay? And it's this sigmoid activation that decides whether the probabilities are sufficiently high that the neuron is now in the fire state. Okay?
How are the weights determined?
So we'll come to that.
So the bias, you just specify the bias are common for all?
No.
Or
So in any neural network, when we have a neuron, that's essentially a set of weights and biases.
Okay.
And part of how you train a neural network is indeed the entire meaning of training a neural network is to find the correct weights and biases so that they give you the behavior that you expect.
I see. So you can specify a bias for all inputs.
No. So this is actually w dot x plus b.
Plus B.
Yeah.
Okay.
So the bias is just a constant.
Because this is one, but if you have like a multiple layers in the center, then the weights.
Yeah.
Okay, I see.
Yeah. But any single neuron.
So if I have two
Yeah.
things here,
Yeah.
then this will go to here, then this will go to here, then I have to specify two biases.
No, if you have two neurons, you can have two biases.
Two biases.
Yeah, but
Okay,
you can with one neuron you can only have the one bias.
Okay.
Yeah.
Okay.
Right. Okay. So because we were also talking about this, right? How would you train a neuron? So the important thing is, suppose this was one of those things that identifies numbers, right? And it can only identify up to maybe 4, right? 1, 2, 3, and 4. That's all it can identify. And then this would shoot up to be high, essentially firing, or 1, when this is 1, when the number that is fed in is 1, right? And then it's supposed to be 2, 3, 4. But to begin with, it would be, when you just randomly initialize the weights and biases, it wouldn't work, right? It would be wrong, right? But then, you would know that, okay, what I've fed in, so this would be what is called supervised learning, right? Where I know what I have sent in is a 1, right? But it's not worked out at all because it's an untrained neural network, but it will say something, right? It will be, maybe it will identify it as a 2 with probability like 60%. So it will say something. Backpropagation is a way of taking the error from one training sample and then figuring out what to do to the weights and biases so that that error is reduced. The thing is, you could, okay, as a brute force idea, right, you could try the following. You could just say, okay, let's go and find all the possible weights and balances for which I get the correct number here. And I say, okay, it's a 1, it says 1. So, but just think of the space of that search, right? So that would be a weight and a bias for every edge. Sorry, a weight for every edge and a bias for every neuron. And now you've got to find, now that's the size of your sample space, right? Backpropagation is actually a way of doing gradient. So there's this technique called gradient descent in numerical optimization. So backpropagation is actually an intelligent gradient descent which takes the error and tells you exactly which weights and biases to move by how much to reduce the error. Okay, so it's basically, you make an error, you notice the size of your error. Backpropagation is a really fast way of changing only the few weights and biases that has the maximum impact on the outcome that you're trying to get correctly. Now, I will not go into the mathematical details of it, but it is essentially an exercise in calculus and linear algebra. It's rather relatively simple. In fact, as I was saying, there's this very nice YouTube channel called 3 Blue 1 Brown, and he has a 2-part video on backpropagation. Both of them are not more than 10 minutes long. Okay, one is probably like 15 minutes long, and one is 10 minutes long. But together they're less than half an hour for sure, which goes in to, so they're chapters 3 and 4 in his course actually. So, and chapter 3 is just an intuitive understanding of what is going on. chapter 4 is actually the entire calculus of what's going on. So in less than half an hour, you've nailed it down.
I'm just laughing how you said both are not less, more than 10 minutes.
Okay, that's yeah. But it's great fun actually. And actually, let me just shout out to the channel. Apart from just this one thing, it's the most fun way to learn math on YouTube, in my opinion. It's just amazing. And nothing is basic there. Nothing is like, oh, I already knew this. It's not like math for 7th class. It's more like fun math, like how to count numbers, for example.
Is there a notion of prior in this back proposition?
No.
So when you
In this sense, no.
then how do you judge that error is just?
Oh, so that comes in the training step, in the sense that when I feed in a 1, in the case of supervised learning, I know that it's supposed to give me a 1.
Is
But-
that a prior?
No,
Oh.
a prior would be encoded in the network itself. This is more a prior on the data set. Like I know this is a 1, but it's giving me a wrong answer.
Can you just specify what does a prior mean here?
Actually, to be precise, in the study of artificial neural networks, a prior means nothing. Yes, in the study of artificial neural networks, a prior means absolutely nothing. So, in real life, it is a question of the weights and biases.
There is no proper back propagation.
Yeah, so there is actually a very interesting debate in the field of AI about whether the brain does backprop or not. Okay.
Well, the consensus was it doesn't, but maybe I'm wrong.
Yeah, so there are some people who would say something like it does something that is mathematically similar to backprop, but it's not actually backprop in the way that we do it. So yes, Josh.
So is backwards propagation just a clever way to do gradient descent?
Yes.
Or are they, okay, so
Yes.
it's the same idea, but it's just
exactly the same
computationally
idea. Yes.
nice
Yes.
way to do it.
And it's not computationally nice in general, actually. It's computationally nice in a very specific way, which makes a lot of sense. Now, I will go to why that is. Okay, so the main thing, and in fact, we'll talk a little bit more about it later, but there was a moment, and in fact, there was a moment when things changed for neural networks, actually. Because for a long time before that, everybody thought that neural networks were essentially useless. Because it was incredibly difficult to train neural networks. So if you think about it, yes, we have this universal approximation theorem, right? We have a reason theoretically to believe that whichever you want, I can do with a neural network. But where the rubber meets the road, the problem is I've got to find a way, relatively efficiently, to find these weights and biases so that I would be able to do something with the neural network. Which in fact leads you very nicely to a simple problem. A small neural network for which I would be able to find the weights and biases using some way is useless. And a large neural network, which we have some reason to believe would work, is untrainable. So we end up in this catch-22 where I can train a small neural network but I can't do anything with it. And I know that I could do something with a large neural network, but I don't know how to train it. Right?
Because in the large, is it because in the large neural network, the computational requirements for the Hessian gradient is too large?
So think about the size of the search space, right? For every neuron you have something like this, right? It has 1, 2, 3, 4, 5, 6, 7. So that's 7 parameters plus a bias, 8, right? The moment you have more layers, the number of parameters blows up.
That's right.
To give you a sense of what I'm talking about, so you remember when...
So they do a grid search. Is it?
sorry?
Is it like a grid search?
No, it's not like a grid search. This is way more intelligent than a grid search because I get from just how wrong I am and in which way, I get a clean way, linearly in fact, per sample. It's linear in the number of samples. I get a way to know exactly which biases and weights to change by how much. So before we knew how to do this, it was not possible to train a neural. So this is one of those moments wherein it's really an algorithmic innovation. But nothing in the field of neural networks is really that straightforward. Even that algorithmic solution, like the idea of backprop is like 25 years old, right? The thing that happened was, so okay, as Josh said, right, is this just a fancy way of doing gradient descent? Like, and I answered that with a short yes. Right? But the thing is, you see, if I could just still do one sample at a time, right? Now I want to predict whether this is a 2, then I need to figure out, okay, how do I do 3? Right? It would still take a lot of time to train on enough 2s, 3s, and 4s to get the neural network trained up. If there was a way in which I could get 2, 3, 4 together into the neural network and then do a training run, right, that would be where the speed ups would be seen. That would require some notion of parallelization. So in fact, most of the compute advantages that led to neural networks becoming practical were in fact directly the mathematical result of us being able to do more than one thing at a time on a CPU. In fact, not a CPU, a graphics card, because the main difference between your typical traditional CPU and a graphics card is that a graphics card is something like 5,000 slow processors, whereas a CPU is like 16 fast processors. But here, because I'm talking about getting a large amount of training data, each training exercise is not that hard, actually. So if I could do 5,000 training exercises at the same time, now suddenly it has become possible to train really large networks, right? So this is this idea called batching. So I would take a batch of training data, or a mini batch, for example, that's what it's called. So I take a mini batch of training data, pass it through the system of backpropagation, whereupon it now becomes something called a stochastic gradient descent, where when I pass 2, 3, 4, and 5 together into the neural network, I am no longer minimizing the parameter losses according to the actual gradient, but rather some kind of average gradient which would minimize the losses for all of these 4 samples together. But that's more of a stochastic approximation to the precise thing to do, which is to minimize them one by one. But as it turns out, the stochastic approximation is good enough, and this, in fact, is a purely empirical fact. It could have gone really either way. And if it had gone the wrong way, we wouldn't have half the things that we have with neural networks. But we're very lucky that it went a certain way. And it so happens now that we are in a position to train really large neural networks. To give you a sense of how large, some say that that GPT-4's parameter space is 170 billion parameters. Okay, so that's like a really large model. Okay? Okay, so that is basically a small. So as I said, the main points are, yes.
Would you be talking about transformers data?
Yes,
Okay.
yes. So the main thing is that it's fast, and also that it's parallel, so it's fast, and it needs a loss function, so you know exactly what to minimize, so it's fast. So the whole thing is basically about the fact that it's fast, because if it's not fast, we can't do anything. Might as well go home. Right? Everything goes to fast, basically. All right. So as I was saying, this watershed moment, right? So there was this image recognition challenge. It's called ImageNet, right? And this was the moment where time turned, actually, because it was AlexNet, which was created by these people, Alex Kozetsky, Elias Esteban, and Dr. Hinton, and it had an error rate of 15.3%, which was more than 10.8 percentage points lower than the runner-up. So this is an image recognition competition. You say, okay, cat, cat, dog, dog, that kind of thing, right? And the primary result was that the depth of this neural network, like it just had enough layers. It was a sufficiently large network, and that is what was essential for this kind of performance.
What is the deep neural network? It's transistors or what?
No, so it is this notion of connecting neurons.
But you don't have neurons in a neural network.
Yes.
What do you have physically?
Oh,
I mean, what's
it's mathematically just, it looks like this, where every single one here is something like this.
But they're like a transistor. It's on.
Oh, I see. So you're asking electronically? They are pieces of code, actually, but they are run on the graphics card. So when you ask transistor, it's more like a CUDA core, which is a core of the graphics card, which is made of like millions of transistors. So every single neuron in this sense requires like many transistors. Yeah. Okay, so as I was saying, the main result was that this is computationally expensive, but it is feasible because of the use of these graphics cards. Right? And this was the moment where things changed for neural networks. Actually.
One more question, just
Yes.
for ignorance. So when they build the thing, they just build layers and layers and they're not sure what's going to happen.
Yes, indeed, yes. In fact, for a long time, they were pretty sure nothing is going to happen. Yes. And at some point of time, it so happened, and in fact, there is a very nice interview of Ilyas Utkiwar in the Lex Friedman podcast, where he's asked, well, you know, AlexNet, right? And then what happened? And he said, okay, look, they were lacking three things. Sufficient algorithmic improvements, sufficient compute, and conviction. Conviction, yes.
Really?
They were lacking these three things, right? So at some point in time, it became possible to have sufficient algorithmic improvements and sufficient compute, and yet they were lacking conviction. But he goes on very clearly to point out, you see, that was not some kind of irrational belief like, oh, why would it not work? It was reasonable to believe something like it would not work because it had not worked till then, right? If I have a pile of apples and I keep cutting every one by one and they are all rotten, and I tell you, no, you know what, the 154th apple is going to be fine. You're going to be like, sure, get out of here, all the apples are rotten, right? Because the first 153 were rotten. And yet somehow the 154th apple was not rotten because they got to it in time.
In some metaphoric way, I can imagine if God were creating the human brain, that makes it very, very complicated, and then he's surprised when the Mozart symphony comes out.
Exactly.
What year did that?
Yeah, go on then.
What year was that?
2000 and
I've forgotten this one.
early 2000.
I would not like to speculate. Just check AlexNet on Wikipedia. The year will be there.
At the time. Around 2012, I think.
Yeah, probably 2012, around that time.
Because it was an undergraduate, I remember. Undergraduate, 2012.
That's interesting. That less than 12 years ago. Right?
Now it is.
Yeah. And now this kind of thing is code that you can run on your cell phone. Anyway, right, here we go. Okay. It's a very brief detour, and the only reason I make this detour is because before LLMs were a thing, right, most people thought the profound achievement in AI was something like AlphaGo or AlphaZero, right? That was sort of the last time we heard of AI killing a giant, so to speak, right? Okay, so that's a little bit different from this. Do you remember that when I was describing how we would use neural networks today, I was talking about supervised learning, right? There's a loss function. How far away from a 2 am I when I am shown a 2? Right? You say, identify this 2 and something's wrong with it, how far away am I? Right? Now, the story that I'm trying to tell with this slide is that when you have a well-defined mathematical loss function like that, life is easy. Right? You know how far away you are. Take a game of chess, though. Right? There is a lot that happens before you won or lost. Right? In fact, your position is improving, your position is getting worse. There seems you would have to judge how is that a good position, is that a bad position? Sometimes it's straightforward, sometimes it's far from trivial. Right? Do I sacrifice a bishop for a knight? Would depend on whether I expect a position, let's say 20 moves later, to be more open or more closed, and things would change here.
So when you say supervised learning, means to say that I give a set of data, then the neural network.
No, and I know both the input and the expected output.
And the expect. I need to know.
I need to know the expected output. That is supervised.
Knowing the output. What's the difference between knowing the output and knowing the expected output?
Oh, you always know the output because if you feed it into the neural network, whatever comes out is by definition the output.
Okay, sorry. The expected output, which means the right answer.
The correct answer.
Okay, I see.
Okay, so yeah. So if you know both what is wrong and what is right, you are able to calculate an error.
Okay.
So the issue with something like chess is really hard to calculate or to even define the notion of what is the meaning of an error, right? Which is where so that's where reinforcement learning comes in, where you have self-play. Essentially, you have two copies of the same robot playing against itself, right? And then you ask the question of if I evaluate a position this way, or if I evaluate a position in another way, which of those leads me to win more often? Really, the only metric that you care about in chess is winning. Right? You really don't care whether your rooks are on open files or not. It's nice, it's written in a chess book. But I don't really care. I care about winning the game, right? And that's when, that was the key difference between AlphaGo and AlphaZero. In fact, for a lot of people, they kind of just remember those things together as one big thing that Google DeepMind did. But there was a very subtle and very important difference. AlphaGo was trained to learn from human strategies in the game of Go, right? So that's what it did first. And then it learned how to play, like, some improvement from self-play happened. But a lot of the early training of the AlphaGo neural network was based on the strategies of human beings, actually, before that. AlphaZero, and in fact it was called as AlphaZero because of this, started from no knowledge of the game of chess. In fact, if you look at the first few games of AlphaZero, it's horrible. It goes on for a few hundred moves. They don't know what they're doing. It's just totally random play.
So they're not digging in any previous games.
Yeah, yeah. And you would imagine that that would be a strange thing to do, because why not make use of everything that we have learned? Yeah, so here's the short answer to that, because everything we have learned was later shown to be full of holes and assumptions, which if you just throw away that previous knowledge and start tabula rasa, you can really get something fancy out of it.
So reinforcement, is it the idea that you give like you write an algorithm with a reward system, if you do more of this, you get more rewards, then you...
The entire fight is about what is the appropriate reward system. Because you see, what is a loss function, right? In the example of identifying digits.
And
Right?
so you do something in expectations, you do this, then your expected reward is there.
No.
No.
So if you construct the reward by yourself, that's a loss function.
Okay.
If the reward comes from nature, in the sense of the game's outcomes are the only things you care about, win, loss, right? There's something different between specifying the loss function myself, like, make sure your pawns are closer to the center, or something like that, right? That could be a reward function. But that's arbitrary. The question is whether you win or not. That's natural to the game.
At least in the early stages, was there ever a point in which the thing really gave an outcome? Where you put a difficult problem in and just set up that?
Yeah, absolutely. Absolutely. But when it's learning from self-play, it gets better and better and better and better with every iteration. And in about 8 hours on DeepMind's supercomputers, it was better than humans, and in about 16 hours, it was the best chess entity, as they called it in the paper. They called it the chess entity in the world. Right?
In chat today, yesterday, I asked it to graph something, and it couldn't do it. And at some point, it just said, "I'm not capable. Come back later tomorrow."
Chat is fundamentally very different. We'll get to that. Yeah.
So is it like something like, okay, you just tell it whether to win or not, right? And then it tries something, then it tries this
then
weights.
it looks like, oh, I lost. Then it changes something.
Then it changes its weights again.
Yeah.
Oh, then after that, it says, oh, these are the
This
rules.
is better. Yeah. It's a little bit like a blind person trying to find a door. If you do sufficient random things, you find the door. And then, oh, I found the door. That's something feels like worth remembering.
In the chess, all the designers have to specify is that a rook can move L shape upon.
Exactly. Only the set of legal rules is fed in. Only the rules of the game. No knowledge about the rules. Right? Okay. And so this kind of thing. Yeah. So there are ways of doing it. Basically, some balance of exploration and exploitation, in the sense that sometimes you need to use the knowledge you've gained so far. Sometimes you need to go out there to find new knowledge. And you have to very cleverly balance both, because if you did only exploration, you wouldn't learn anything. If you did only exploitation, again, you would miss out on things that you haven't tried out, which might be good ideas, but you don't know that. So yeah, there are some policy and value networks. In fact, a lot of reinforcement learning gets very close to Bellman equations and dynamic programming, actually. That's why you see things like I have a policy and a value network, right? So this is a typo. Yeah, and as I said, and size, right? Because that's everything in neural networks. Like, it's about speed and size. That's it. And you can't get speed because you need size. You can't get size because you need speed. When you can get both of them together, now you have something that you can sell to us. But again, yeah, as I said, size. That's it. All right. Some of you have seen some reinforcement learning projects before, like my collusion paper, for example. That's a very similar idea. The agents start with no idea of how to play this game. But they price together, they see the profits, and they say, oh, okay, let me try that instead. And that's how they learn, and yeah.
the rap models of reinforcement learning, they learn fairly quickly.
Oh, you mean like rat slam, like
I
the
mean, you know what
like the
reinforcement
rat.
is in biology.
yeah, exactly.
So like you put a rat in a cage with two pedals,
Yeah,
and one of the pedals will give sweet milk and one not,
yeah.
and they learn very fast.
They learn very fast indeed. Yeah, for sure. In fact, there have been attempts. In fact, when I was working at Honeywell, we used to do this where you would check a neural network built similarly to a rat's brain and ask it the question of, as I said, the model is called rat slam. SLAM stands for simultaneous localization and mapping, where the question of whether when you are running around a place, right, you are actually doing two things. One is you are always answering the question, where am I? And what is around me? And actually the answer to where am I, when integrated over a sufficiently long period of time, is what's around me, actually. Right? And that's why the mapping problem is simultaneously a dual of where I am and what is around me. And in fact, these rat brain-based neural networks are excellent at solving mazes and things like that, which can be very useful for all kinds of navigation problems, actually. So in engineering, we have looked at these kind of questions of whether we can do things using, ideas derived from biology, like for a while. Because in engineering, it's very nice. There's no dogma. If it works, you can market it as a product. So that's nice. All right, let's. I know that you basically get, all of that is just like sort of history, right? Because something happened in 2017 and that changed everything else. So kind of all the old stuff doesn't matter. But I will take one parting shot at this idea, which is that actually transformers have less than nothing to say to the question of reinforcement learning as of now. You just have that somewhere in your mind, because reinforcement learning continues to be something where we have no good way of making progress. It's just these small, tiny improvements that we are aggregating. Why is that?
Almost the dumbest, most primitive animals can learn reinforcement.
Yeah. Oh, no. We can match the dumbest, most primitive animals for algorithms. That's not the problem. The problem is that most of the things that we are wanting to do with reinforcement learning require fundamentally a loss function. And reinforcement learning, the loss function is so far away from every decision you make. Like, you finally, it's like, oh, did I get the apple or not? If you really think about it, the kind of grasp motion that babies can do, right? When you toss something and it can catch it, right? This kind of, they are training it for like years, right? And every movement is training, right? But we want to get there like that with the neural network, right? So the challenge we are setting these things is also quite a bit harder in some senses, at least in the temporal sense. But yes, now let's just talk about large language models, right? So, okay, and everyone's heard of this. The modern implementation is basically everything's around this idea called a transformer, right? But first, what was there before, right? Surely the first large language model was not started after we made transformer, right? There is autocomplete. How does that work? Okay, so this is the idea. The previous state of the art is something called a recurrent neural network, RNN. Okay? What is a recurrent neural network? Essentially, it has an input layer and output layer, and this is important, a sufficiently high dimensional internal state, plus the idea, so as I say, it processes words sequentially. The idea is that the updation rule of the neural network is Markovian. Markovian, in the sense that I look at one input token, like some word, showman is, right? And now I must finish updating the neural network before I can process another word. Because showman is cannot be fed in together into the neural network.
So it's like you press F, then the next letter is U, then it tries to predict the
yeah.
Okay.
Exactly.
Then the Markov process goes.
Exactly. Right.
So which means to say that there's no training. It's already all pre-trained, is it?
Oh, when you use it, yes, but during the training process also,
Okay,
the training samples can only be sent in one by one.
Okay, so for the user, this autocomplete is already
pre-trained.
It's pre-trained, so
yeah. Well, you could technically add some words for yourself and things like that, but that's just like it just has access to a dictionary. You're just adding to the dictionary. So except in that sense, it's pretty clear. Yeah. Okay. And so the issue is it processes words sequentially, and then therefore training is slower. And what do we know about things being slower? The size has to be reduced if it has to be practical. And what do we know about small neural networks? They belong in the trash can. Right? So that's how it is. Right? So because the effect of one sample on the network must be finished before accepting the next sample. So there's a fundamental limitation. Yes.
This is because of the internal state needs to be updated.
Because the fact that the state is really high dimensional. And in fact, even if the state is low dimensional, you would then run into more problems because the network becomes smaller. But fundamentally, the updation rule is Markovian, in the sense that before I can tell you how a sample would pass through the network and give me what on the output, I need to have the network in the configuration that it would be in if the previous sample has been fully processed. So it is sequential. That is fundamentally the issue. Right? And so as I said, serial nature also removes much of the performance gain from using the graphics card. I can't do anything with 5,000 cores if I can only use one of them at a time. Right? So no point. Okay. So what is the question is why suddenly? What happened last year that we suddenly have things like GPT 3.5, right? ChatGPT. What happened? Right? And the point here is that we suddenly found a way to have parallelization, to be able to do multiple things at once, to be able to configure the neural network in a way with a lot of information beforehand. So when I ask for something new can be given to me instantly. Right? Okay. So we'll just go through what is language models process sequences of words represented as grids of numbers. So this is the key point. Okay. But I guess it's not. Let's see if I need to write. Okay, I can gesture a lot. So the way that it's going to be is that in column major order, right? There is a matrix. Okay, every column of that matrix is a word. Okay? Every row of that matrix is some parameter of the meaning of the word. So for example, things that are related to water, for example, bottle, river, and duck, right? In the parameter that talks about water, in that dimension, they will be relatively close to each other. So these words are imbibed with as many as 4,000 to 8,000 points of meaning. So a word is a point in 8,000 dimensional Euclidean space.
And this is sort of pre-trained in a sense? No.
So you could do that. So there is an old way of doing this where with programs like WordVec, you would be able to get a pre-trained dictionary of these words, right? But
is the wording association? It doesn't come from the dictionary. It comes from usage.
Yeah. So yes and no. So it also answers Josh's question that you could do that. You could make it with a dictionary. Right? There is one way of doing that with just using, let's say, something like Oxford Advanced Learner's Dictionary, right? Or you could just keep these as free variables, which will be fixed during the training process.
And that's what's happening. So these are
GPT-4, that's what's happening. Yeah. So with like the new crop of large language models, that is what is happening.
And so there's no necessary way to interpret like row 1. I couldn't say beforehand, row 1 is going to do like how wet is this object,
Yeah.
Okay.
Not now, but in previous programs like WordVec, you would be able to. Because what you would do is you would collect all the words that were related to water, plot them together in like this high dimensional Euclidean space, and look at various slices of that space and see in which dimension they cluster together best.
And then that would
probably
be
water. Right?
Yeah.
Yeah.
But why can't I? So I just trained this. I don't know how it's going to be trained, but so you do it, and then I say, okay, here are all the water words, and then
you could probably do exactly the same thing. Yeah. Except you notice that if I leave that choice free, the resulting error rate will have to be lower than if I consider it, whatever the training process is, right?
Oh, sure. But I guess my question is that beforehand we have no way of knowing what attribute 5 is going to be. And after the fact, we might be able to figure out, we might be able to interpret
Certainly.
these things. But,
Certainly.
yeah, okay.
Okay, so now we have, as I was saying, each row represents a measurement of a property of that word. Okay? And words with similar meanings have similar numerical values across rows. So the rows are some parameters of meaning, the columns are the words, right? So you have this giant matrix, right? So a dictionary is created during training, as I said, mapping words to numerical columns. So every word corresponds to a certain choice of column numbers, right? Okay. So as I said, in column major order, these are words from left to right. Alright. So context and dimensionality. The grid, this grid that I have been describing, is actually what is called the context. Okay? And it spans several thousand columns, which is words and rows. Okay? So context length, when interesting, context length is actually this dimension of the matrix, like the number of columns in the matrix. In the case of the largest context models, for example, Claude, is 200,000 words. Okay? So it can hold in mind 200,000 words of 8,000 point each. Right? And then you have here.
So it actually does words, not tokens.
Oh, so here, just to keep things simple, I'm thinking of a word as a token. But yes, indeed, it actually does tokens. Yeah. Okay. Context length is, as I say, is rapidly expanding. Early models like GPT-2 had like 8K context. Even today, for some smaller models, it's quite common to have only 8K context. Okay, so now you have this, the row count actually is more or less fine. There's not much point in adding more meaning to every word. It has been discovered. You just add, more parameters is the way to go. Apparently.
So this,
Yes.
is this parameters?
No.
No,
This is not really parameters. This is sort of, it's the number of input neurons. It's not even exactly that, but it's something like that. In the sense of how big, how tall is my network? Like how many things do I put into it at one go? Right? So this is more like that. It's a context. Right? And then each layer performs a mathematical transformation and passes the grid to the next layer. Okay? So each layer of the neural network does some calculations with this context and sends it to the next layer. Okay? Most systems have between 64 and 96 layers. Okay? That means there's 96 hidden layers in the middle. In GPT-4, for example, Zero says it's about 96 layers. So 96 layers in the middle of this extremely high dimensional object being passed through to generate the output. Okay?
I'm sorry.
Hmm.
How is this number determined? I mean
You mean
the number of
the
layers.
layer depth?
Yeah.
Typically a question of at what level do you start seeing declining returns to scale. Like if you have, let's say, 64 layers and your next word token accuracy is 99.4%, now you have, let's say, 70 layers, do you see like 99.6% or 99.41%? Right? So you know where to stop. Because at any moment there is a cost of adding an extra layer, because it'll extend the training duration. On the other side, you gain something in accuracy. Fundamentally, it's not very different from the way in which you choose the number of parameters in a regression. I'm sure you're familiar with the notion of R square and adjusted R square. Right?
Alright.
That's the same.
I see. Thank you.
Okay. So okay, after processing through all layers, a new column of numbers is generated. That is in fact what all of this neural network is supposed to do. Right? You feed in this context, it'll at the end of all of this calculation, it will give you one column vector. That's all it does. It gives you one column vector. Using that column vector, you can predict the property. So you can pick the word in the dictionary that is closest to this column vector. That's your next word. Remove the first column from the context, add this column to the context, go again, and you have a large language model, right? So that's how you're doing this prediction, basically. Okay. Now, okay. So this is a very controversial question, right? I thought, let me take a stab at it on the sake, because that's just, for those of you who know me, that's just the way I run, right? So, okay. So, think about it, what is the loss function in a large language model, right? The loss function in a large language model is that when I make this prediction, right, in the beginning with an untrained neural network, it's likely to be quite lousy. Now, I have, based on the training data, I know what the next word is supposed to be, at least in the training sample, right? So I have two vectors, prediction, truth, like ground truth, what it's supposed to be. I can subtract them and now I have a loss function, right? At the moment I have a loss function, I can do high dimensional backpropagation, like stochastic gradient descent, and I have a fast way of training this network, right? And now, so again, what is the loss function? The loss function is how far off am I in terms of predicting the next word, right? Now, so the question I ask here is there understanding of the word, right, in a large language model? So as I said, on the face of it, it is trained merely to predict the next word, right? So some have even called it a glorified autocomplete because of that reason. It seems like that's what autocomplete does, it just predicts the next word. Many are confident that an LLM cannot be creative because of this loss function. Right? So, because it just feels like, okay, I just want to predict the next word. There's something seemingly trivial about that endeavor, right? But is this really true? Right? Now here's the thing. One way of looking at the exercise of training, right, is that the more training data you have, the fewer possible choices of parameters there are that actually work within the training set, right? So because every time you add another training data, it is something that is constraining the set of choices further. You cannot keep having more and more parameters in spite of having more and more training data. But the core idea is what is training data, right? So when you look at, let's say, what OpenAI trains GPT-4 on, right, it's things like Wikipedia, it's things like the Encyclopedia Britannica, it's things like, apparently, every Reddit comment that is longer than 3 words. Right?
New York Times.
Oh yeah, sure. Okay, yes. So, but you know, if you look at these things, right, what is contained in that, right? If I can accurately predict everything that the New York Times article is going to say, or the Wikipedia article is going to say, and I can do this over a sufficiently large amount of data set, is it really likely that I can do that while not encoding any actual information about how concepts in the word, or the words, right? Because every word is associated with a concept, that doesn't mean language, right? Is it really possible that I am very good at predicting the next word in out-of-sample situations, like outside the training set? I'm very good at this, with having really no way in which a bicycle and a monkey are linked together, right? But I argue that if for sufficiently large amount of data, sufficiently large amount of training, this is not possible, right? Because fundamentally the weights and the biases in a neural network encode the way in which concepts in the world are linked together. So when you say sky, dark, rain, okay, that's the way in which, that is the information that is actually being encoded into the weights and balances. To which I say that the way in which we encode knowledge is also mappings between concepts, actually, right? And fundamentally, therefore, at least in the way that knowledge is encoded, there is no difference between an LLM in this mode, right, and us. So then, if you have a sufficiently large network, the model has to understand the word in order to maximize coherence across arbitrary contexts with the same model. Because you see, I cannot keep changing the model. This is my New York Times model, this is my Wikipedia model. It's not really like that, right? It's the same model. And I need to encode all this knowledge into these weights and biases so that regardless of whether I'm in Wikipedia or I'm in a New York Times article, the next word is right. And I can only do that if I actually know something about the word. So this seemingly trivial loss function of I just want to predict the next word, right, is not an Achilles heel of the large language model. Indeed, I prefer to call it lightning in a bottle. because it is this loss function, and in fact this choice of loss function that changes it from an autocomplete to something that actually has understanding of the word. Creativity is a completely different question. So that, because we would have to get into exactly what is creativity, I would argue, okay, you try new mappings of concepts and you know, oh, okay, did this work, did this not? Potentially with reinforcement over LLMs, you could probably even do creativity, because creativity is, this you would have to sort of, there are multiple opinions on this, but one possible school of thought is that creativity is guided experimentation. You try something, doesn't work, you try something, it doesn't work, and then you build an idea of what might work, right? And then that's how you do that. So yeah, just to take a position.
But the model doesn't, can I be critical and say,
Yes, please.
the model doesn't have to understand. The model has to have an understanding of the world.
Oh, that's completely different things, for sure, I agree. All I'm saying is there understanding in an LLM, right? Does it, so to the sense, okay, that would be the question of whether an LLM is an active agent in some sense, right? But no, in that sense, the only agency that an LLM has is minimizing a loss function, right? And to the extent that it is only minimizing a loss function, of course it cannot understand something, right? Except in the way that it's minimizing the loss function, right? Okay, its agency is limited to only that one parameter. But if you are talking to it, it is very, very good at pretending to be like someone who has an understanding, who in turn has an understanding. And I want to be very precise here that the word pretending does not take away anything from the actual knowledge that is encoded into it. Right? Okay.
I mean, many human beings pretend.
Yeah. Frequently.
Yeah.
Okay. So does an LLM understand everything? No. Only to the extent that something is captured in language. Right? If concepts are captured in language, that's the only thing it understands. An LLM will never be able to do that. Okay? Because it has no idea of what just happened, right?
But it understands mathematical language? I mean,
If you train it, it understands code, for example.
And it understands symbols.
Yeah, certainly.
You just make the distinction between understanding and understand.
No, Gavin made.
Okay.
If anything, I
You share
counteracted.
this.
No, I share it in a qualified sense. I think Gavin got what I mean by in the qualified sense.
I got
Agency.
that distinction, yeah. So that's what Richard has said, right? You have an understanding of that.
I think it's not central to Richard's question. Richard, can you repeat your question once for me?
My question is it at a deep level of understanding? Will it recognize mathematical symbols?
Oh, yeah,
and
certainly.
use them as like words?
Yes. In fact, you can ask a model to write mathematical equations, formulae, things like that, and it would write coherent mathematical symbols and formulae, even out of context, like things that it has not seen in its training data. Because it's actually using understanding from language, because fundamentally its understanding is at the level of concepts, right? So it can leverage that action from the context, from the concepts, and now all it needs is a mapping between concept and mathematical symbology in order to make outputs that are consistent with our mathematical language. So this would be how you would train a neural network.
But it could invent a new kind of mathematics. Could it go from...
I addressed...
Could it go to solid geometry?
I addressed that separately in the question of creativity, right? So the question would be, if an LLM were to be required to do something like that, you would need to give it the same kind of training that we get when we learn to do something new. How do you learn to do something new? No, you do. You do very much know. For example, how do you learn to drive, right? You try something a little bit, and the person who's teaching you says, "Oh no, that's dangerous. Don't do that. Do this instead."
Do we know how we are created?
How we're created? No. Oh, how we're created? Oh yeah, certainly.
How we are.
No, so what I'm saying is, indeed, there can be multiple views on how we are creative, but at a minimum, experimentation is required for creativity. And an LLM has no, in the training process, there's no emphasis on experimentation at all. Again, why? Because the loss function does not properly capture rewards from experimentation. Because an LLM's training is all in its brain, right? It has no interaction with the real world. So in fact, I was going to come to this point. Jan LeCun, who is chief AI scientist at Meta, argues that we are fundamentally on the wrong track with LLMs. So there's a very interesting debate between Elias Skiver and Jan LeCun, where one of them is like, yeah, we just have to feed enough knowledge into this thing, and it's suddenly going to light up and it's going to become creative and everything. Whereas Jan LeCun is like, no, you could keep feeding all the knowledge that you have into this, and it would still never make anything new, right? And he, in fact, argues that we would have, before it can make anything new, we would have to embody it and put it into the real world. So it would have consequences from experimentation, both positive and negative.
So is this the idea of reinforcement learning?
So this is something that they talk about, again, as I said, in this podcast with Les Friedman and Jan LeCun. They say that an LLM embodied in a real world with a certain reinforcement learning loop, now there is really very little reason to believe that it cannot be creative. Because it can try things, and now suddenly it knows how to try this. So just give you an example of something that is actually insanely creative is AlphaZero. Right? So both me and Gavin play chess at a reasonably high level, and for those of us who understand how AlphaZero plays, right? When you see those games, there is no doubt in anyone's mind anymore that it really understands what it's doing, and it's able to play in a way that in terms of raw creativity surpasses anything that any human has ever done, and anything that we have seen these superhuman chess engines do for the last decade. Like, computers have been better than humans at chess for 10 years now, and like the best pre-neural network engines were just extremely good bean counters. Like, they were going to grind you to the ground with skill. Like, there was something different about the way that AlphaZero plays chess, actually. Like, it just throws away material with a wild abandon, in the sense that I will just lock you down in a situation you cannot move at all, actually. Right? This is not the way that the previous chess engines used to play. So when you see that gap between a very, very good computer and something truly out of this world, right, it's clear that there is a certain kind of creativity, at a minimum, baked into AlphaZero. And what is the difference between AlphaZero and an LLM? Right? Is reinforcement learning. It's basically is the key that you try something in the world and you know what works, what doesn't, actually. Right? And based on that, even if you look at the MCTS, right, the Monte Carlo tree search, and especially the policy network, it knows to explore strange ideas. There are books actually that have been written after the AlphaZero thing on how exactly it learned to do that. And if you see, it actually explores. It knows to explore strange things, not sort of the run-of-the-mill. The policy network would suggest sacrifices first. Like, hey, have you considered sacrificing your queen yet? It's always thinking about how can I sacrifice my queen. It is a strange thing to do. Why? Because it knows that in many positions, you just have to sacrifice your queen and everything falls into place, right? And it's like, yeah. So it has that bias towards flavor, actually, like in its play. Right? It, in fact, is more creative than human beings in that sense, because it is fundamentally looking to play chess like a drunk person all the time. there's that tendency of animalism in it.
Okay, very good. You don't mind.
Yeah.
I noticed you did share Gavin's distinction between having an understanding, and then just now you used understand directly as a verb.
Yes, in case of that,
yeah,
that thing I would say.
I'm just trying to pin you down that when you do so, that you are aware you're doing so.
Yes, very
and
much.
also when you say creative, you mean it.
Yes.
Even though sometimes I get the impression you're saying that as if.
No,
you mean it.
I mean very much that these LLM models are an as-if model.
Okay.
But something like AlphaZero is totally
creative.
Yeah.
Then it begs the question of definition. What is creative?
I could sidestep that question by saying
Okay.
something like LLMs are not, and anything with reinforcement learning is likely to be.
Okay, so it's an operational statement. So
yes.
you're-
Yeah.
I'll just leave
It's
it
probably
there.
not very satisfactory, but of course we can revisit that later.
Okay, cool.
Yeah, okay, we are almost to the end. Okay, so there was of course some intention of talking about what we can do with these models. This is relatively boring, but we'll go through it very quickly. So one of the things that you can always do with the current crop of AI tools is some degree of literature review. So as you want to get started on something new where you do not know the literature, right? And this is a great place to start. So an ideal candidate would be a web-enabled service, such as ChatGPT or Bing. Both of these can search the internet, as opposed to Claude, which cannot search the internet. Okay? So you can say, okay, go out and find me some papers regarding this and that, and then it would find you a paper and some papers, and then usually you can go from the references of that paper and open your tree for searching, things like that. Okay, this is one of my favorite things to do. So I work in a very narrow area of economic theory. I have no need for literature review. Most of the things outside my field I cannot do, and most of the things inside my field I know.
I just did something. I didn't realize I can actually. Do I need to disconnect?
Yes.
Okay.
Imagine.
I thought it doesn't take
The AI is
over.
taking over.
Okay, I'm an AI. Alright, I'm out now.
What do we do?
He's not really out.
I feel like I'm out. Oh, I'm not really out. How do I get? I press disconnect.
No, I suppose you just disconnect.
Yeah.
He's disconnecting, but it's not disconnecting.
It's not disconnecting. Oh, disconnect. Oh, okay, back.
Disconnect.
Mm.
So, I just want to see. Oh, no. I still hear.
Okay, you know what? You guys figure it out. You don't need the slides for this bit, right? I just talk through it. Okay.
Just talk through it.
So the other good thing that you can do with LLMs is brainstorming, right? So as I was saying, as I attempted to establish previously, although arguably, is that AIs have a fundamental understanding of the world. So often they can be used as useful tools for a limited amount of brainstorming. Right? So you can say, hey, do you think this idea would work? Or is this an equilibrium proof? Something like that. And this, though, requires some, like, there is a certain benefit from having a large context for this kind of thing. So I suggest that you use something like Claude for this. So Claude is not connected to the internet, but if you can feed it with everything that it needs to know in order to talk about your question, it just upload all the papers that you need, right? And then say, hey, based on these papers, do you think this or do you think that, right? You'll be surprised the number of times it actually makes a sensible, reasonable answer. Right? And of course, that would mean that you have all the things that you need in order to ask these questions. If you don't, then you just you need to use something like ChatGPT, because then it also has access to the internet. Right? And then coding. So coding is something that these LLMs were trained to do from the ground up, and it can they can actually code incredibly well. But this part is interesting. Do not try to code something that you do not know how to code by yourself, unless you're trying to learn something, because they make mistakes. And if you get like wrong code, it can be incredibly difficult to find out precisely where it goes wrong if you haven't written the code yourself. So at best, write code where if you read it, you would know that this is the place where it's wrong. So it's like a labor-saving device. It's not really like, I have no idea how to do this, let me just ask you to write a code to take me to the moon. That's not going to work, right? So something like that, right? Okay, and
It's also good at making your code more efficient.
oh yes, it's also very good at making your code more efficient. So just to give you a sense of, for the longest time, my anti-pollution paper was just a theory paper. Like, I was still very proud of the mechanism itself, but I just thought for the longest time that I would not know how to code that in reinforcement learning. And how that project actually happened was that I asked Bing to write me a reinforcement learning algorithm to play tic-tac-toe. And then I was able to just take that code, understand it, modify that for my purposes. So you know that feeling that you get when you're just starting something new and you have no idea, 0 lines of code on the editor, right? It's a good way of breaking free from that. You just get something to start with and then you start modifying, and that's kind of nice. So of course there are many, many other uses, just any number of other things that you can do. That was all I had for the presentation, but in fact, we thought that there could be more Q&A, and I'm very happy to answer anything today. But of course, other people are also.
A lot of Q&A so far.
Yeah, other people can also answer questions. Yeah, George, please.
Can I just ask a concrete question about Transformer?
Yeah, please.
So if I asked a question like, what color is an apple? What color is an apple is my question, and then it gets a context. So I don't understand how it works basically. So there's a context thing, and what happens?
Color is an apple.
So I gave it a couple of words, and so it pulled out those. So I drew a picture of the context thing. It says word 1, word 2, and it's got some attributes. And so then it would find the words that I just said, and what would it do with those words? Or how does it know what word to find next?
So what it would do is it would take those words, right? Oh, I should say one thing. So you see that the thing is, really there are two modes in which the LLM exists. Right? The first is like, I've given it some text. Now I need to sort of predict the next word that would follow after the text. But the short answer to questions like that, what color is an apple, is not like what would be the next word in this question, right? So then there is usually a step after this where there is a sort of a network so there is a sort of there's a network that contains the LLM, in the sense that it asks the questions, and then if you get the correct answer, then the question is whether the answer is appropriate for that. So that's where the people at OpenAI who were doing the human training, right? Is this the correct answer or not? Is this the correct answer or not? That sort of thing. So that's sort of the query network in some sense. And then what happens is when you put that query, like what it does is it's like, it picks up the operative words from your question. Indeed, the operative words are color and apple. And now it's trained beforehand to answer questions as a helpful assistant. Like, yes, dear Josh, an apple is red in color, right? And then somebody before that said, oh yes, if you talk like this, is good. But the fact that an apple is red in color is actually coming from the training set, where it's like an apple. So when it starts to write an apple, now it's like it is red in color.
Okay.
Right? Based on the context, yeah.
So a lot of how it replies is just hard coded in a sense. Like, so be a polite.
Not hard coded. It's coded. It's again a trained neural network. So it's a neural network that runs another neural network in the background. In the second neural network that is running is GPT-4.
But the transformer part is the thing that found that apple and red are linked.
Yes.
So there's another neural network that's like be a polite, write a polite response to Josh.
Yes.
But then the transformer says apple red or something like that.
Yes, precisely. That's why the knowledge is encoded.
And so to get apple red, what did it do? It starts with this big context, right? And then it finds the word red, it finds the word apple.
It starts with the sentence, an apple is, and it has a sense of I'm talking about the color of the apple, because it's there in the context window. And then it's adding words as I described the context window flows through the network, next word.
And we'll pull out a next word and it'll be like, oh, okay, so red is relevant.
Yes, it's a property of an apple. So that is what I mean by these concepts are coded in the weights and biases of the actual neural network.
Thank you.
Thank you so much.